William is a PhD student researching microplastics in coastal environments where his studies apply sedimentological processes to understand where microplastics are sequestered. So today he's going to be talking to us about searching for microplastics and in coastal environments, leaky lagoons, and sticky shorelines. So over to you.
Thank you, Catherine. Very happy to be here. So my presentation today is going to take us on a field trip to the Texas Gulf Coast, where we're looking at a series of coastal environments. Mainly my research focuses on bays, lagoons, estuaries. I'm calling them bays today, as well as the barrier islands that protect these shallow water environments. And we chose to target this particular system because in the geologic record, these bays are known to be sediment traps. And given our increasing coastal populations, they act as filters for terrestrial derived material as it's working its way towards the coast. And microplastics may be sequestered similar to sediments. So, as a geoscientist, we're taking our understanding of sedimentology and sediment transport to better understand how plastics may be sequestered in these environments because we care about these environments specifically along the Texas coast because it's a huge industry for tourism and shrimp and oyster fishing. So to better understand this system and how microplastics may be sorted, we're looking at rivers and currents as sources, and then key drivers such as winds and storms as routing them through the system, and then other processes that may be relocating them and reducing their preservation potential is either shoreline erosion or resuspension. And in order to address these questions of where microplastics may be forming hotspots along the coast, we're employing multiple techniques, starting from the ground, where we're collecting sediment samples and water samples, and then we're taking them back to the lab and doing particle analysis of the microplastics as well as the grain size or the bed material that they are sequestered in, and then taking a bigger picture approach of using remote sensing and numerical models. And so my environment is known as Matagorda Bay. It's including in three different bays: San Antonio, Matagorda, and East Matagorda. We have principal river discharges in here, making it a bay, and it's separated from the Gulf of Mexico by a thin sandy spit. And it's important to note that we have a prevailing onshore wind orientation in this system. And it's a very shallow water environment, mostly less than 2 meters, which becomes important when we think about winds and frequent storm activity. So I began my research with collecting over 100 sediment and water samples to get a baseline quantification of how much microplastics are in the bay sediments, because our budget suggests that there are millions or even billions of microplastics sourced to this system every year. We have a unique system here that it has a microplastic manufacturing facility, which is this red star, that's been spilling into this environment for tens of years, and they've documented their material all along the shoreline. So we know that it's there. We also have material sourced from almost 30% of Texas coming down the rivers. And we wanted to see how much is actually being preserved in our bay sediments, because this can pose risks to organisms that we ultimately are harvesting. And so what we did was we went out and collected sediment grab samples and push cores. We separated the microplastics out from 100 grams of sediments, and we quantified that for mass, as well as we measured the size of the plastics, the grain size of the bed material, and the organic material as proxies for if it relates to a particular grain size, such as silt, or a particular density, like organic material, or water depth, distance to shoreline, distance to anthropogenic centers. We wanted to see if there was a spatial pattern. So this is our results. So these are microplastic counts per 100 grams per location, where I've pieced out the different types, which I've categorized as fiber or fragment. And what we see here is kind of an ambiguous pattern. There's not really a correlation with water depth, or I don't have it here, but there's no correlation with grain size or organic material. And so there's something else going on here, as well as the general trend in the total microplastics that we found. It's much lower than what we expected. The most was around 30 particles per 100 grams. And we also didn't find any of the raw microplastic material that has been spilling into this environment. So there's something else going on here. And so our model that we came up with to explain these results was these microplastics that we found. They are generally much larger than the grain size of the bed. Our grain size of the bed is generally silt. Our grain size of the microplastics are usually 3 to 5 times larger than that of the bed. And so we're explaining the lack of correlation with any of these other proxies in that these microplastics are much larger and less dense or more buoyant. And thus, when we introduce any sort of currents driven by wind in this particular environment or storms, they would be preferentially remobilized and put into the current and transported uh, in the orientation of the currents. And in this scenario, we have a prevailing onshore wind 10 months of the year. And this can explain why we see more microplastics along our shorelines within the bays. And then we also have a daily ebb and flood tide. We can see material sourced offshore during just normal scenarios, and then large amounts of material that's being sourced offshore, specifically during storm activity. So when we go in looking at the bigger picture of using remote sensing data, we can see enormous amounts of resuspended material routed through the environment quite rapidly. So these are planet daily scenes showing on the left an ebb tidal plume of large amounts of material exiting the ship channel. This is just during normal scenarios. And then on the right, this is a more extreme scenario. This is after Hurricane Harvey in 2017, where a Category 4 hurricane came across this study area and induced a significant or 1,000-year precipitation event uh, and caused a large amount of material to be sourced through the fluvial environment, as well as resuspending a large amount of bed material, estimated up to 10 centimeters. And so when we think about the relative mobility of these microplastics, this may explain why we're not finding as much, because it's quite mobile and it's routed through the system quite rapidly. So these storms can act as key events of flushing microplastics through the system and ultimately to the Gulf of Mexico or to our shorelines. So to summarize the first part, our lagoons not as sticky as we thought they would be, as the geologic record would suggest. So we want to look where we see a lot of plastic debris, which is our shorelines. And we want to think about these storms as key events when this plastic is mobile. So I was somewhat fortunate that a big storm did occur during my PhD program. This was Hurricane Beryl, which came across the study area last July as a Category 1 hurricane. And so we wanted to go out and collect field data and couple that with our remote sensing data to analyze how plastic debris or marine litter is deposited uh, due to a storm, and how barrier topography controls where this debris is routed and ultimately deposited. And so we have a very unique data set that's coupled with this. We have a pre and post storm LiDAR data set that we can ultimately use to map these litter deposits. So this is some of the data that we collected. Our storm path came across the study area in East Matagorda Bay, impacting the Matagorda Peninsula as a Category 1. Here on the right, I have just some textbook examples of the landfall of a hurricane, the buildup of the storm surge, and the passing of the eye of the storm with the wind. And we collected data over this 30-kilometer beach transect. Here I have some of the data we collected. We took a drone and collected an orthomosaic where we can map the plastic-rich deposits. We have GPS field locations where I'm where we walked the beach and took a point and measurement where all of the most plastic-rich deposits were. And here on the right, I have some of these observations. What we found was a lot of plastic debris that was concentrated within vegetation rack lines, which indicate the high water mark of the storm surge. And these were usually onlapping the preserved dune topography or protruding vegetation. These were quite interesting as it seemed like the vegetation was ripped up by the storm surge and impacted a barrier. And as these dead grasses accumulated, they seemed to form a sieve or a filter for everything else that was suspended in the water column and filter it out and form these very plastic rich deposits when we had topography or vegetation. And conversely, when we didn't have preserved or pre-existing topography, these plastic-rich deposits were much more diffuse. So what we want to do now is use this pre and post-storm LiDAR data set where we can measure the freshly deposited plastic-rich deposits and link that with a systematic control of barrier topography and vegetation and illustrate and quantify where the plastic was deposited. We can also use the bare earth digital elevation models to show where the most sediments was eroded or deposited, and that can also be linked with plastic being preserved. And in the case of erosion, we can tell a story of plastic was removed and either deposited in the bay through overwash deposits or returned to the Gulf of Mexico through return channels. And lastly, so we didn't find as much plastic in the bays. We see a lot of plastic deposited due to storms along our shorelines and the barriers. Now we want to link all of this together and ultimately calibrate a numerical model to seed particles during a range of scenarios and figure out where these microplastics may be forming hotspots that might not have been at the resolution of our field sampling. And these can be calibrated with all of our grain size and organic material, hard data sets to build a model that we trust. And ultimately, we want to be able to apply this model to understudied regions where we don't have the capability or the funds to collect this much data or the time, and ultimately inform potentially at-risk coastal zones relatively rapidly. So this is an area that we're pursuing at the moment. And as a concluding slide, seen a lot of great presentations today, and there's many more scheduled. I'm having a GSA session in October, and I would love that we could do this again. And I'm happy to answer any questions.